Welcome to another episode of learning. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of the problems that have appeared in the CSIR National Eligibility Test, July 2025. In this video, we discuss the solution of a problem from the section Complex Analysis, and it is related to the evaluation of a contour integral. This question is placed in part C, which is a multiple select question. There may be more than one answer and it carries 4.75 marks. The question ID is 562954156. Further, this question is suitable for all these examinations. Right. The given question is, let gamma be a map from the closed interval 0, 1 to complex plane with the function defined by t mapping to e to the power of 2 pi I t by gamma, and I, the integral, is equal to integral taken around gamma of the function e power z into e power minus e to the power of 1 by z. I is equal to integral taken around gamma of the function e power z multiplied by e power 1 by z with respect to z. Which of the following statements are true? We are given four options. Option 1, I is equal to 0. Option 2, 1 by 2 pi I times I belongs to the set consisting of 4n, n belongs to z, n greater than or equal to 4. Option 3, I is equal to 2 pi I multiplied by sigma n is equal to 0 to infinity 1 by n factorial. Option 4, I is equal to 2 pi I multiplied by sigma n is equal to 0 to infinity 1 by n factorial into n plus 1 factorial. Right. Let's now discuss the solution of the problem in detail. We are given the contour gamma of t is equal to e to the power of 2 pi I t, where t belongs to the closed unit interval. That is the closed interval 0, 1. And what is it? It is a unit circle centered at the origin, traversed once in the counterclockwise direction. That is, gamma, in other words, is mod z is equal to 1. Right. Where we are asked to evaluate the integral. I is equal to integral taken round gamma of f of z dz, where f of z is the function e power z multiplied by e power 1 by z. We observe that f of z is equal to e power z into e to the power of 1 by z is analytic everywhere except at z is equal to 0 because of the presence of e to the power of 1 by z in the function f of z. Right. That means to say that z is equal to 0 is a singularity of the function f of z, and it lies inside the unit circle gamma. It's in fact the center of the unit circle. It lies inside. Right. To determine the nature of this singularity, we write the Laurent series expansion of this function f z about z is equal to 0. f of z is equal to e power z into e power 1 by z. For e power z, 1 plus z square by 2 factorial plus so on and so forth, multiplied by 1 plus 1 by z plus 1 by 2 factorial z square plus 1 by 3 factorial z cube, etc. etc. Now, this product has infinitely many terms with negative powers of z. Now, you see 1 times of 1 times 1 by z, 1 times 1 by 2 root 2 z square, so on and so forth. And many more, even from z contribution also, many more negative powers of z will appear in this expansion. This product has infinitely many terms with negative powers of z. We mean to say that the principal part of the Laurent's expansion has infinitely many terms. This means z is equal to 0 is an isolated essential singularity of f of z. Right. We continue in the next slide. Right. We have seen z is equal to 0 is an isolated essential singularity of f of z. Now, the integral I is equal to integral taken around gamma f of z dz is equal to 2 pi I times residue of f at z is equal to 0 by Cauchy's residue theorem. By Cauchy's residue theorem, 2 pi I into sum of the residues at its isolated singularities that lie inside gamma. But there is only one isolated singularity, that is essential singularity at z is equal to 0 that lies inside gamma. So 2 pi I into residue of f at z is equal to 0, where res f comma 0, how the residue of f at 0 is calculated in the case of z is equal to 0 is an isolated essential singularity. Then what do? We get into the Laurent series expansion of f of z at z is equal to 0 and take the coefficient of 1 by z in this expansion, and that will precisely give you the residue of the function f at z is equal to 0. So I is equal to integral taken around gamma f of z dz is equal to 2 pi I into residue of f at z is equal to 0 multiply 2 pi I into 1 by z, that is 1, z into 1 by 2 factorial into z square. Z into 1 by z square will give 1 by z. From here 1 by 1 factorial into 1 by 2 factorial, this one, plus z square by 2 factorial into 1 by 3 factorial into z cube. Z cancels, the coefficient of 1 by z is 1 by root 2 into root 3 plus so on and so forth. That is the coefficient of 1 by z in the Laurent's expansion of f of z about z is equal to 0. This is equal to 2 pi I in the sigma notation. Sigma n is equal to 0 to infinity 1 by n factorial into n plus 1 factorial. It's precisely this one. You can check it. Right. Let's look at our options. This is our answer. 2 pi I into sigma n is equal to 0 to infinity 1 by n factorial into n plus 1 factorial. That is precisely I, and that appears against option 4. So the answer to this question is option 4. And further, note that none of the other options, that is I is equal to 0 and so on and so forth, these three values, none of the other options is equal to 2 pi I into sigma n is equal to 0 to infinity 1 by n factorial into n plus 1 factorial. Thereby, the options 1, 2, 3 are not true. They are not the solutions. So, the only solution is option 4. So, the answer to this question is option 4. That is the detailed discussion of the solution of this problem from the section complex analysis, and it is related to the evaluation of a contour integral. It's not a surprising question. It is a regular routine question, right? And I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. Please subscribe my channel if you have not already subscribed. Yes, I am sure I will meet all of you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.